In this example, we've been given a right triangle and told what two of the sides are. B is 4 and C is 6. We're interested in finding alpha, beta, and the side C. So first thing I'm going to do, like I did in the previous example, is organize my data first. Oh, hi, BB. I love when she shows up for videos. So gamma is across from C. That's our across from the hypotenuse. That'll be our 90-degree angle. We'll label the two sides that we do know. We'll call that 4 and 6. Now with that in mind, if I'm interested in finding our last side, I already know two of the sides, so we can find A using the Pythagorean theorem. So A squared plus B squared is equal to C squared. We'll plug in the two quantities that we do know, and we'll solve for what we don't know. Oops, that should be an equals 6 squared. That'll be A squared plus 16 is equal to 36. Subtract 16 from both sides, and take a square root. Now normally, when we do this with angles that are in standard position, we have to pose the question of should this be a positive square root or should this be a negative square root? Because we are dealing with triangles, it will always be a positive square root since we're dealing with lengths. Now, our exact answer would be 2 square roots of 5. If you're interested in getting a rounded answer, you can certainly plug that into the graphing calculator. Bless you, baby. Poor thing's sneezing down here. Rounding that at the second decimal place, I would call that about 4.47. But if you need to reuse A in any calculations, I would recommend sincerely that you go back to the exact version. Now, as far as finding angles is concerned, I would really like to try to relate these angles to B and C. For example, if I'm interested in solving for alpha, from the perspective of alpha, B would be the adjacent side, C would be the hypotenuse. Because we have adjacent and hypotenuse, if I'm interested in finding alpha, I could point out that the cosine of alpha is equal to B over C. Or rather, the cosine of alpha is equal to 4 over 6. Reducing that, we get 2/3. To finish solving for alpha, we take an inverse cosine of both sides. Now that, again, would be our exact answer. This does seem like a situation where we would want an approximate answer as well. So, the arc cosine of 2 over 3, according to the calculator, and we did verify in our last example that this is in degree mode, that would be about 48.19 degrees. And we'll mark that up here as well. Now, as far as how to solve for our last piece of data, we have a couple options for how we could do so. One method that we could do is exactly what we just did, using beta as the angle, and try to relate beta to B and C. You'll notice that from the perspective of beta, B is the opposite side and C is the hypotenuse. So you could use the sine of beta is equal to B over C, which again is equal to 4 over 6, which we reduce down to 2/3. And beta would simply be the inverse sine of 2/3. And according to the graphing calculator, if we were to do so, the inverse sine of 2/3 would be equal to about 41.81 degrees. However, there is another method for if you already know one of the angles, how to find the other angle. So we'll point out, or we could just say that alpha plus beta is equal to 90 degrees and plug in what we got for alpha. So beta would be equal to 90 degrees minus alpha, which is 90 degrees, minus 48.19 degrees, which by some amazing coincidence happens to be 41.81 degrees. I wanted to do it a couple ways just to demonstrate that there is more than one way to approach these problems. And if another way makes a little bit more sense to you than the other, then I would say go with that method.